Welcome to a screencast on the periodic property of atomic size. If we try to determine the size of an atom, it turns out that's quite difficult to do because an atom consists of a nucleus surrounded by an electron cloud or electron density that doesn't have a very sharp edge. It's kind of fuzzy, and the fuzziness of an atom's electron cloud makes it quite hard for us to determine the exact size, such as the radius or the volume of the atom. So how do we do this? What do we do to determine an actual value for the size of an atom? Well, we pick the radius typically as the thing that we measure, and we define a thing known as a covalent radius by taking two identical atoms, bonding them together, and if they're bonded together with a covalent bond, we measure the distance between the two nuclei. And that's actually something that can be measured quite accurately. And so we then define the covalent radius of an atom as half the distance between the two nuclei if the molecule consists of two identical atoms joined by a covalent bond. So that is a radius, it's half the distance between these two nuclei, or that is the radius, half the distance between the two nuclei. And again, this is something that can be measured quite accurately. So what sort of trends do we have in atomic size? And we're going to pick radius to measure. And if we look at trends across the periodic table or throughout the periodic table, we can either go across a row or we can go up and down in a column. And let's look for the trends in each of those separately. And we'll first do a group or column, and we're going to pick the alkali metals as our example. And we're going to use three alkali metals. First of all, lithium. It has a positive 3 charge in its nucleus, 3 protons, surrounded by an inner shell of 2 electrons, and then an outer shell which has 1 electron in it. The next alkali metal, sodium, has 11 protons in its nucleus, charge of plus 11, 2 electrons in the first shell, 8 electrons in the second shell, and then 1 electron in the third shell for sodium. And then let's do one more. Potassium has 19 protons surrounded by 2 electrons in the first shell, 8 electrons in the second shell, 8 electrons in the third shell, and then 1 electron in the fourth shell. So in each case, we have 1 valence electron, and we have a nucleus surrounded by 1 or 2 or 3 inner shells that are filled. And if we look at the attraction of the outer shell electron in our very simple model here, with lithium, we have 3 protons or positive 3 charge surrounded by an inner shell of 2 electrons or a negative 2 charge. And the net effect of that, of the 2 electrons shielding the nucleus from the outer shell electron, gives us an effective nuclear charge of about 1 on a lithium atom. And that effective nuclear charge is what's attracting that outer electron. For sodium, we have a positive 11 due to the nucleus, surrounded by 2 plus 8, which is 10 inner shell electrons, which of course are negative, and 11 minus 10 gives us also a plus 1 charge for the effective nuclear charge for sodium, with the nucleus surrounded by 2 inner shells of electrons shielding the nuclear charge from the outer shell electron. And exact same idea, but with different numbers for potassium. 19 protons surrounded by 2 electrons in the first shell, 8 electrons in the second shell, 8 electrons in the third shell, 1 valence electron in the fourth shell. That also gives us an effective nuclear charge of plus 1 because 18 electrons in inner shells are shielding 19 protons in the nucleus. And it's probably pretty obvious what effect this has on size. A second shell that has a valence electron versus a third shell versus a fourth. Well, lithium has a radius of 152 picometers measured in this way. Sodium, with 1 more shell but the same effective nuclear charge, has a much, much bigger radius, 227 picometers. And potassium, with a fourth valence shell that has an electron in it has an even bigger radius, 248 picometers. So our general trend is, as we go down this column in the periodic table, the alkali metals, the atoms get gradually bigger. They get gradually bigger because as we go down the group, we have more electron shells. We have valence electron shell that is larger because we have more of them, and the valence electron shell determines the size of the atom. The effective nuclear charge is about the same because even though the nuclear charge increases as we go down the column, we have also an increased shielding effect, and they basically cancel each other out. And therefore the atomic size, and here we're using radius as our measure, increases as we go down the column. And in fact, if we look at the periodic table as a whole, we find the same trend in each column. Gradually get bigger for the alkaline earth metals as well. If we stay with main group elements and you go down column 13 or 14 or 15, etc., you find that we have gradually increasing size of atom because the effective nuclear charge is about the same, but our size determining valence electron shell is farther out. It's a larger electron shell. Now, what about trends if we go across a period in the periodic table? And as our example, we're going to use the third period. And again, we'll pick a few elements out of that third period. And the first one is aluminum, positive 13 nuclear charge, surrounded by 2 electrons in the first shell, 8 in the second, 3 in the third. We have 10 inner shell electrons shielding a positive 13 charge from the nucleus. So now we have an effective nuclear charge of +3, and that is attracting these 3 valence electrons. The next element we'll use is phosphorus. It's a little farther across the period in the periodic table. 15 protons in the nucleus, 2 electrons in the first shell, 8 electrons in the second shell, so 10 inner shell electrons as with aluminum, but now there's 5 valence electrons, and what that means is we have 10 inner shell electrons shielding 15 protons, gives us an effective nuclear charge of +5, attracting these 5 outer shell electrons, and the larger effective nuclear charge essentially pulls in the electron density of the outer shell electrons. So even though there's more of them, they're actually not as far away on average. And so we actually have a smaller atom for phosphorus than aluminum, even though it has more electrons, because it also has a larger effective nuclear charge. And if we go to chlorine, 17 protons in the nucleus, surrounded by 2 and 10 in the first and second shells respectively, and then 7 valence electrons for chlorine. The shielding from the 10 inner shell electrons surrounding 17 protons gives us an effective nuclear charge of +7. That's even bigger than the +5 effective nuclear charge for phosphorus. So again, even though there's 7 valence electrons, there's more valence electrons. They are pulled inward, or the electron density is drawn inward more due to the larger effective nuclear charge, and so chlorine is smaller yet. And here are the actual sizes. Aluminum, 143 picometers for its radius, phosphorus, 104 picometers, and chlorine, 99 picometers. And you might notice, as with the trend going up or down a column in the periodic table, it's not exactly linear. It's just a gradually increasing or decreasing trend, but the changes in radius aren't the same from, in this case, aluminum to phosphorus as it is from phosphorus to chlorine. And if we look at this general trend for the third period in the periodic table and kind of summarize going across the period, what's happening is we have the same electron shell for the outer electrons. We have an increasing nuclear charge and roughly the same shielding due to inner shell electrons. That gives us an effective nuclear charge that increases as we go from left to right across the period. and that increasing effective nuclear charge makes the atomic size or the atomic radius smaller. So atomic radius decreases going across a period. And if we look at the periodic table as a whole and look at other periods, we see the same general trend. Let's not pay too much attention right now to the transition metals. They don't follow the trend quite as well. For the main group elements, the same electron shell, but increasing effective nuclear charge means that we get a size decrease going across the row of the periodic table. Now, let's look at this for our kind of final thing here. Let's look at this graphically. And if we graph atomic radius versus atomic number, what we should see is as we go across the periodic table, as we go from across the first row, we should see size decrease. But then when we jump to the second row, we go to a farther out shell, so we get a big increase. And then as we go across the row, the size should decrease again. And that should just keep repeating itself as we go across the periodic table. So let's see if this follows. Hydrogen to helium, first row, slight decrease in size. Big jump to lithium, we go to the second shell. Gradual decrease, not perfect trend, but gradual trend of decrease from lithium to neon. Then we go to sodium. Now we've started the third shell. Gradual decrease down to argon. Big jump upward in size to the fourth shell with potassium. Gradual decrease going across the fourth row. Notice it gets kind of out of whack with the transition metals, and we're not going to try to explain that right here. Then we go from krypton to rubidium to the fifth shell. Big jump in size. Gradual downward trend with, again, the transition metal elements not at all as clear or predictable. And then we'll do one more, xenon to cesium, and we're starting the next row, and it goes downward again, and the trend continues. We've only shown about the first 60 elements so far, and that is it for periodic properties, or the periodic property of atomic size.